Hello, everyone. It is the Prophet Michael David, aka Aries, and I hope everyone's having a great day. So I'm trying to get more efficient. So this is just an add-on video explaining some stuff that I wanted to explain in the last video, but I got to the 12 minutes, so I couldn't. All right, really quick recap that you can learn more about in last video. The prime number theorem was discovered by Carl Friedrich Gauss. And if you do it the way that I do it, it's equivalent to saying that the nth prime number is somewhat equal to, as n goes to infinity, n times the ln of n. So if you use a simple spreadsheet and you graph them on them, they look like this. But what I found was, in this context, there is a much better line, discrete line, that tracks the prime numbers, and this was the equation that I came up with. And if you type that equation to your spreadsheet, you can see that it follows the primes much better than Gauss's n times L of n line. Now, if you graph these three columns together, the primes compared to the others from 2 to whatever prime is under 25,000 will look like this. And at the end of the spectrum, for the numbers I did, the prime numbers for the last from 400,750 to 500,000 will look like this. Okay, for clarification, these aren't like 25,000 primes in a row. The first one is the primes from 2 to 25,000, and the last one's from the primes from 475,000 to 500. I got the primes off the internet in a text file, and they're in segments of 100,000. So I decided to segregate those up into quarters. That's how I did it. And so these last two screenshots just show you that each increment of primes in between 25,000s is about 2,000 primes, and gradually over time it does go down. As you can see, my line is always closer than Gauss's line, but my line is always over more than the prime line, which means my estimate will be more primes than there actually are. Where Gauss's line is always under and much farther away, and compared to my line, grossly underestimates the prime line. So you can see that even in a density case, my line is much better at estimating how many primes up to infinity. But then I noticed and pointed out that that last variable that I ended on or attached to Gauss's equation, natural log of pi, which approximately equals 1.1447 something something something, that if that pi dropped by a minuscule amount over infinity and eventually got to e, then natural log of e is 1, and my line would become the prime counting function, or the prime counting theorem. But what I did not detail was that you can use the primes themselves in an analytical sense, not a predictive sense, to calculate what that variable v would have to be at each prime and how it would change over time. And if you do that, you use this equation. And finally, if you do that and you watch how v varies over the first 500,000 primes, it looks like this. As you can see, that variable drops very quickly down to around pi and then flatlines, but it doesn't quite flatline. It does decrease over time, although very, very slowly. As I said in my previous video, it's difficult. You're trying to bound an integral transcendental infinity between pi and e, and you're trying to couch that inside a discrete summation which goes from 1 to infinity. So hopefully this has clarified my equation a little bit. For you mathy people, you may totally understand, but for the layman's, maybe not. Let me explain it this way. I couch the prime numbers in between two different lines. So really all you have to do to find the secret of the prime numbers is find some equation that drops either from pi to e over the course of a natural infinity that matches, that pretty well. Or if you deal with the whole equation itself, ln of v, ln of pi as it goes from pi to e, that value goes from 1.147 something 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 to 1. So however you want to do it, either with the natural log or with the actual variable inside, if you can do that, you can find an estimate for the primes, which with only natural numbers, you're not using previous primes, that tracks better than the Riemann hypothesis. It would be the best predictive model ever created by man. All right, again, this video was longer than I thought it would be, but they always are. That's why I have to make extra videos. As always, do not hurt each other and try not to lie. And my next video, I'm pretty sure, is going to be addressing the tribe of Judah. And that's probably going to be tomorrow, even because it's Sabbath. Unless she doesn't want me to, because it's Sabbath. But other than that, you'll have a good night. I'll talk to you later.